Hello, class, and welcome to part B, or the second part of our first week's lecture. Here, talking about measurements in chemistry. Much of what we'll do in this class is going to be qualitative, meaning that we're going to be learning concepts, describing how electrons and protons and atoms behave, using very more so descriptive language. Of course, a core part of chemistry and science in general is the quantitative side of measuring things to try to figure out not just uh, is there carbon present, but how much carbon is there present in the atmosphere? What do we use to measure it? How precise or certain are we of those measurements? And we'll dive in right now. So, as I said in our part A of this lecture, scientists are really interested and really particular about describing things. And so you may encounter, a vial, a little jar of pink powder. And the natural question is, what is this thing? How do we as scientists describe these things in ways that maybe a normal person or someone who has not gone through this type of class, how would they describe it? Well, I think naturally many people would use a qualitative descriptive. A description that is qualitative is one that might use words to describe a property. So you might say that this powder is colored light pink, or this powder is finely textured, very many small particles. These are qualitative descriptions, which are important in chemistry, describing what things look like, how they behave. We might also use comparative qualitative descriptions. We might say that this powder is denser than water. If we notice that this powder sinks in a cup of water, we'll be able to infer something about its relative or comparative, making a comparison density more dense than water. Scientists, however, need to, and in many cases are able to go one step further, making a quantitative description, in many cases a quantitative description of the same properties. So a quantitative description, a quantitative measurement, is going to be something that can be measured on some sort of scale. It might be a physical scale like you would have in your bathroom to measure your mass or weight, but it might be some other scale like a temperature scale. Every quantitative measurement, every quantity is going to have two parts to it. There's going to be a value, which is going to be a number, and we'll say more about sort of how many digits in those numbers there are, plus a unit. Nearly everything, with some exceptions, has a unit associated with it. A unit may be something like a kilogram being a unit of mass, a second being a unit of time, a meter being a unit of length. For example, this powder, by saying it's light pink, we can qualitatively describe its color, but we can be even more precise, more specific about this description by assigning a quantitative measurement to it. Color is often measured by an RGB value, sort of the intensity of red, green, and blue colors in that material. And so we might say that this powder has a quantitative color of 255, 182, 193, representing the quantity of each of these red, green, and blue wavelengths. We may also say, instead of saying it's just finely textured, which is a more general qualitative description, we may say that the average particle size is 0.01 millimeters. Here again, we notice that we have a value, 0.01, and a unit, lowercase m standing for millimeters. We may also, again, make comparative statements, saying that this powder has a density of 2.2 grams per centimeter cubed. Again, we see a value, 2.2, and a unit, now here a compound or more complicated unit, grams divided by centimeters cubed, but no less measuring a scale or sort of a relative scale for this quantity. Now, as chemists, we go even one step further than most scientists. We're concerned not just what things look like, how much it weighs, what color it is, but we want to know what these materials are composed of. What are they made out of? In this case, this particular light pink powder is a mineral. It's a rock composed of many different elements. In this case, K for potassium, Li for lithium, Al for aluminum, Si for silicon, O for oxygen, F for fluorine, and H for hydrogen. We would write a chemical formula, which we'll learn more about in a couple of weeks. But this gives us a precise idea of what this material is made out of, what elements are found in this pink powder. And as again, another peek toward the future, We might even use something like a CAS, a CAS number, which sort of acts as a barcode for every chemical in the known world. Most often in science, we're going to be using metric prefixes, and this is generally also true of medicine these days. Uh, Historically, the US has used standard or imperial units, things like pounds or inches or feet, and those are slowly getting phased out to be consistent with the rest of the world, which uses metric prefix or metric units, things like meters or grams. The beauty of these metric prefixes, or sorry, metric units, is that every denomination of mass, for example, is separated by a factor of 10 or factors of 1,000, giving us the ability to easily convert between large and small values of the same unit. We utilize a series of prefixes that modify this base unit. So here in this table, we can see that if we wanted to measure the mass of something, we might measure in terms of gram, this lowercase little g. 1 gram is not a lot of mass. It's a kind of a small amount of mass, probably the size of or probably the weight of a coin or so. If we had something very, very large, like a person, people would be thousands and thousands, thousands and tens of thousands of grams. And we could easily equivalently say, instead of saying 10,000 grams, we could say 10 kilograms. A kilogram, this kilo prefix, meaning 1,000 grams. And so we use these prefixes to sort of eliminate unnecessary zeros. It gives us easier units to work with, allowing us to talk about really large amounts of mass, things that are gigagrams or megagrams, or things that are very, very small, milligrams, micrograms, and nanograms, each of them related by a factor of 10, in many cases separating them by a factor of 1,000. We should be comfortable using both this table, but eventually we will begin to memorize these prefixes and they'll come second nature. And there is ample opportunity to practice this in problem set 1. And of course, we will be using this skill throughout the rest of the course. So definitely make note of this table. This table is a fantastic thing to put in a cheat sheet and one that you will need to reference time and time again. We apply these prefixes largely to make the numbers easier to work with. It is equally correct and it is equally the same to say I have 1,000 grams of water, as well as to say I have 1 kilogram of water. They represent the same amount of mass, but potentially it's easier to say 1 kilogram versus 1,000 grams. We don't have to write as many zeros. These metric prefixes modify a series of base units, which we'll talk about a few here. And it's helpful to kind of have a reference point of how large these base units are. So for example, if we measure the length of something, we would likely want to use the metric unit of a meter, measuring length. Depending on what we're measuring, we may want to use a different type of unit. If we were wanting to measure a large distance, like the distance between my house and campus, which is about 15,000 meters, I would probably want to represent that as 15 kilometers or kilometers. Since it's a large distance, I'm going to use one of these larger units. If I wanted to measure the size of a human, a person, which is about 1.5 meters, I would keep it as the base unit of a meter. I probably wouldn't want to change it for a smaller unit, like a micrometer or a micron, since the size of a human would be 1.5 million micrometers or microns. That small unit is much more suitable to something like the size of an individual human cell, which is 0.000015 meters, or more simply 15 micrometers or 15 microns, often said. You can find charts throughout the internet to kind of give you some reference point for how large or how long or how fast or slow each of these prefixes denote. Again, it's helpful to keep in mind that things dealing on the human scale are generally in the length of meters. Things on the molecular or atomic scale are in the range of micrometers or nanometers, 1/1,000,000th of a meter or 1/1,000,000,000th of a meter. If we want to measure mass, which we quite often do in chemistry, we'll use the base metric unit of a gram. And if we want to measure in time, the length of something, or sorry, how long something takes, Our standard unit, of course, is a second, which is pretty universal. Overall, there are many units out there. We see the similar ones over and over again. Meter for length, mass, a gram for mass, seconds for time. As we measure temperature, and we talk about temperature a little later in this course, we will utilize both the unit of degrees Celsius, which is a common metric unit, but we'll also be using this metric temperature of a Kelvin, represented by a capital letter K. Kelvin is related to degrees Celsius. You take the degrees Celsius and add 273.15, a very specific, somewhat random number, to convert that temperature into the equivalent temperature in Kelvin. We do so that we don't have negative temperatures. You can have something on a very cold day. It might be minus 10 degrees Celsius, which would be 263.15 Kelvin. And we'll see later on why it's important to not have negative temperatures. It tends to mess up the math. So we use this unit of Kelvin to get only positive numbers for temperature. We may also have compound units. So something like the volume is sort of the length times the width times the height, which is length cubed. So we might use cubic meters as a unit of volume, or liters as a unit of volume. 1 milliliter is the exact same thing as 1 centimeter cubed, or 1 cubic centimeter, a very handy relationship to remember. Density, concentration, and pressure are also units we will commonly use. And problem set 1 has us do a little bit of a scavenger hunt to look up what the abbreviation for many of these units are, become familiar with the name of that unit, what it measures, whether it's mass or volume or density, since we will be using them without much explanation further on in the course. So it's always helpful to get a good reference point for it. Some tips and tricks for these metric units. Again, this is something that we will practice a lot throughout this course, so it can take some time to become familiar with doing these metric units, and in particular using these prefixes, kilo to modify gram, so on and so forth. But again, problem set 1 is a very important problem set to get practice with this. So of all the problem sets to pay good attention to make sure that you are completing as on time as possible, this is a critical one that we will use throughout the rest of this course. Some things to be careful about when, particularly when writing these metric prefixes. Chemistry is a science in which it really matters whether something is lowercase or uppercase. What I mean by that is that if I were to see you write 1K, 1 representing some sort of value, K representing a unit, K could stand for a number of different things depending on how you write it. If you write a lowercase little k, that is a metric prefix, such as you would represent for a kilogram, a kilometer, a kiloliter, so on and so forth. And that is distinctly something different than a capital K, which stands for Kelvin, this measurement of temperature. Again, we might represent something as a lowercase m, standing for meter, versus, actually a lowercase m, either standing for a meter or the milli unit prefix, or capital M standing for something different. In the case, capital M stands for mega, representing a large version of that unit. I say this since most of our work is going to be handwritten, to make sure that your handwriting can distinguish between uppercase letters and lowercase letters, and that you are very careful about not mixing up the two. I'll, of course, provide some help, and I can usually interpret what you mean if you write something, but this is your fair warning that pay attention to your handwriting. My second tip is that eventually, a lot of these metric units and prefixes will be something you naturally memorize and remember from doing a lot of it. But you're welcome, and it's encouraged for accuracy to look these things up to double check yourself at this early stage in the course. Eventually, you will find that it's faster having already just memorized what a kilo prefix means and how to use that compared to the longer thing of just of looking it up. But you're welcome and encouraged to look things up to double check yourself in the beginning. A little bit of a note, particularly for those of you who were trained and or raised or had your primary education outside of the U.S., depending on where you learned math, and there's really no great pattern, you may use different conventions. You may represent large or small numbers in different ways. In this class, we of course use the American and US convention to denote large numbers and small numbers. In particular, if we want to denote a large number, something that has to be separated by the thousands, we use either a space, so no punctuation, or we use a comma to denote thousands of something. So in this case, you see 10,000 written in one of two ways. Both of those are acceptable. Some places elsewhere in the world might use a decimal point to represent that same notation, but here we're going to use a comma. For us in this class, we're going to use a decimal point to represent things less than 1, so very, very small numbers. Again, you see this decimal point separating the ones place and the tens place in this particular notation for 1/10,000,000th. So make sure that you are denoting things consistently with how we're adopting for this class. If you end up going and working and continuing studies elsewhere in the world, you're welcome to switch to that notation, but at least for here, do use these particular so-called numeral separators. Now, in many cases, if we want to write a large number like 1,000, we would probably simply write 1,000,000. But what if we want to represent a very, very, very big or very, very, very small number that has more than 3 zeros, potentially more than 20 zeros? Let's say we want to count and talk about how many molecules of gas there are in a helium balloon. Well, in a equation or calculation that we'll come to later in the course, you would realize, or I will tell you, that in 1 liter of air, so a 1 liter sized balloon, 1 liter in volume, there's about 45000, many, many zeros. This large, massive, seemingly impossibly large number, this many molecules of gas in this balloon bouncing around as individual particles. Now, at this point, with this many zeros, we don't have as many common metric prefixes. We don't have kilo or mega or giga or exa or tera or whatever that describes and can help truncate some of these zeros. This number is also way too large to plug into any calculator, so we would have a hard time doing calculations with such a large number with this many zeros. In order to still do calculations with this number, what we as scientists use is called scientific notation, where we represent this number as a base number times a 10 to the x exponent. What it means is we sort of divide out all the tens, all the zeros in this number, and set it aside as a separate factor. So we can take this very, very large number, this impressive number of molecules, and we can divide out all the zeros and write equivalently as 4.5 times 10 to the power of 21 molecules. This times 10 to the 21 molecules helps separate out the zeros, and is what we use for scientific notation, dealing with these very, very large, or in some cases, very, very small numbers. Now, with this scientific notation of this very, very large number, it is, one, more compact, easier to write 4.5 times 10 to the 21 than write 4, 5, and 21, or 20 zeros. Not only does it allow us to more easily and more concisely write this number, we can more easily do calculations with this number. So let's say we want to know of all these of all the air molecules bouncing around in this balloon. We know that air is not just composed of one type of compound or element. Air is composed of many things. About 21% of the molecules in this balloon are oxygen molecules, O2. About 21%, or 21% of this 4.5 times 10 to the 21 molecules. We can use this compact scientific notation to do some easier math, saying what's 21% of 4.5 times 10 to the 21 molecules. We can deal only with this small prefactor, the 4.5, do math with it, and leave the 10 to the 21 alone. We can leave it since it is kept out and kept to the side for easy notation. So to take 21% of 4.5 times 10 to the 21, I could very easily plug into my calculator 0.21 or 21% times 4.5, and then my calculator will give me an answer, one easily that I can double check, and the calculator will give me 0.95 is 21% of 4.5. I can leave it in scientific notation. I can just leave this 10 to the 21, all these zeros attached to it, to show it's such a large number, giving me my answer without having to plug in 20 zeros into my calculator. To be most proper with scientific notation, we typically want exactly one digit to the left of the decimal point. So 0.95 times 10 to the 21 is not quite a standard way to write this number. We want to move the decimal place and have the 9 to the left of the decimal place, but still, of course, have the same number. This 0.95 we can represent in alternative scientific notation. 0.95 is the same thing as saying 9.5 times 10 to the minus 1. This minus 1, of course, means basically 1 over 10, or divided by 10. So we can take 0.95, turn it into 9.5 times 10 to the minus 1, all of that times 10 to the 21 molecules. Combining everything, dealing with these exponents gives us a proper scientific notation of 9.5 times 10 to the 20 molecules. Again, scientific notation requires us to adjust these numbers so there's exactly one digit to the left of the decimal place, basically one digit in the ones place. Now, scientific notation is very, very useful. We use it a lot in chemistry since we talk about individual molecules, individual atoms quite a lot. We need to deal with these very, very large numbers with 10, 20, 30 zeros appended to the end of them. But it does require us to have some comfort with exponent-based math. So a quick review, in case it's been a while since we've worked with exponents. If I have 10 to the power of A times 10 to the power of B, I can combine these two together by adding those exponents. So 10 to the power A times 10 to the power B becomes 10 to the power of A plus B. Similarly, if I divide these two 10 to the power ofs, I subtract their exponents, so it becomes 10 to the A minus B. If I divide 1 by a thing, 1 by 10 to the power exponent, that just becomes the negative of it. So 1 over 10 to the A just becomes 10 to the minus A. And if I raise 10 to the A to another exponent, so 10 to the A raised to the power of B, I multiply those exponents A times B. Again, problem set 1 does give us some practice dealing with these calculations and unit conversions, going from kilograms to grams, so on and so forth. So make sure that you are treating problem set 1 with a healthy bit of respect and diligence. Now, most of the math we do in this class is going to follow a very similar set of algebraic transformations. We don't really do complicated math in this class. We don't do calculus. We don't do differential equations. We don't do a lot of abstract two-dimensional math, so on and so forth. Most of it is just algebra. And in particular, we do a lot of math that converts from one set of units to another. In these conversions, by just converting from one unit to another, we're trying not to change the quantity that's being measured. For example, if I wanted to represent my mass, my weight, I could measure that in pounds, but I may want to convert that to kilograms. I still want to represent how much I weigh as a person, but I just want to represent it in a different unit using one of these conversion factors. Commonly, we might convert between imperial units and metric units via a conversion factor, something that describes the relationship between two units. So for example, let's say I was 120 pounds. I'm not really, but we'll pretend for the sake of this equation. Let's say I'm 120 pounds. How much is that same mass, that same amount of weight in a different unit? In this case, a metric unit of kilograms. To convert between pounds to kilograms, I need to know the ratio of pounds to kilograms. This is something that is easily looked up. This is the kind of thing that I don't necessarily need you to memorize. You may begin to memorize some of these ratios as we go along, but this is something that you're more than welcome to and encouraged to look up to be very accurate, and in many cases much quicker. If you were to look it up, you would see that 1 kilogram is the same thing as 2.2 pounds. This ratio describes a conversion factor from kilograms to pounds, or from pounds back to kilograms. Again, all these conversion factors really equal 1. They're a ratio, 1-to-1 ratio, kilograms to pounds. Since we don't want to change the mass of the person that we measured, we just want to change the unit. To convert between a starting unit, maybe something we measure like the weight in pounds, to a unit we care about, the weight in kilograms, most conversions go like this. We start with the value we know, in this case something we measured, 120 pounds, and we map out, we write down where we want to get to. In this case, we want to convert it to kilograms. We then need to gather and find as many conversion factors that we need. In this case, we only need one conversion factor, one ratio, that says how many kilograms are in 1 pound or how many pounds are in 1 kilogram. Both represent the same thing. We write out an equation. We set up an equation. My suggestion is, there's many ways to do this, but my suggestion is you write the thing you know, the thing you start with, 120 pounds on the left, and on the right you set up where you're going, in this case, kilograms. Now, to convert between, you kind of have a choice of whether or not you multiply or divide by your conversion factor. In many cases, most of the challenge of converting factors is knowing whether or not you multiply or divide by a number. In this case, we always check that the units cancel out. What I mean by this is that when we write these equations, we write down the unit, not just the number. We write down the unit. We want to make sure that not just the numbers are multiplying and dividing, but the units multiply and divide. Just as numbers can be added, subtracted, multiplied, and divided, so can units. If I have a pound unit here in 120 pounds, and I divide it by 2.2 pounds, I of course can divide 120 by 2.2, but I can also divide pounds by pound. In this case, the pound divided by pound cancels those units out, effectively negating or getting rid of that unit. I can see that in my final answer, I have 120 divided by 2.2 times 1 kilogram. I have one remaining unit left, kilogram. I've canceled out, I divided out all the pounds unit, giving me some assurance that I indeed should have divided by 2.2 as opposed to multiply by 2.2. This is quite a simple example, and one in which you may find a calculator online that says you plug in 120 pounds, it tells you how many kilograms, but it does get more complicated from here. In each case, the strategy is the same. We want to write out where we start, so the starting value we have, where we want to get to, the ending unit we want to calculate, and we need to make sure we're multiplying and dividing correctly with all these conversion factors, in which case we may have more than one. Quite often in chemistry, in this class in particular, we're going to have very complicated conversions that we're doing. Ones that don't go from mass unit to mass unit, pounds to kilograms, but something maybe more abstract. So let me give you an example. Let's say you wanted to calculate, or at least estimate, how many hours you'll spend on the T coming and going to class this semester. Now, this is definitely something that you might be interested in. We want to know how long we're going to spend on public transport, but we may not be able to measure directly the number of hours we spend on the train. Instead, we could estimate or calculate a much easier thing, something we already know and can count much more readily. In this case, we can measure or count that we want to know how many hours we'll spend in one semester. So in essence, we want to convert from the unit of one semester worth of classes, to how many hours are spent how many hours are spent on the subway coming to class in that one semester. For this, just like we did before, we need to search for a number of conversion factors. Sometimes I'll give you conversion factors. Some might be ones that we learn as a result of sort of the chemical principles. Others you may need to look up. And this is something that, again, requires practice and repetition. So we will ease our way into it. But here's how I would go about attacking and approaching this problem. How do I convert from the unit of a semester, one semester's worth of classes, to a different unit, really any other unit? Well, to get down from a large unit of time, like a semester, down to something smaller, I could say that I know one conversion factor, one one-to-one ratio, is that per semester, there are 16 weeks. Something I know, I can easily convert, or sorry, easily calculate, easily count, something I can look up. 16 weeks to one semester. That is one conversion factor. I know that I have, at least this class, I have chemistry class 1 day per week. And to attend chemistry lecture and lab, I need to make 2 trips per day. I need to come to class and I need to leave class to go back home. Finally, I can make some estimate that there's about 30 to 50 minutes per trip. So I'll take an average and say each trip on the subway is going to take me 40 minutes on average. And then finally, to get to my final desired conversion factor, or final desired unit, I can put in a definition, which is best just that there are 60 minutes per hour. No estimates, no guesses there. That's exactly how long an hour is. So finding all these conversion factors takes some skill, takes some practice, but nonetheless, it's something that allows us to convert between quite dissimilar units, a semester versus hour, using this methodology. So let's plug this all together. We have found all of our conversion factors, as many as we need, and we're going to lay out our conversion factor equation. We're going to start on the left with the unit that we know that we've measured, 1 semester worth of classes, and we're going to sort of lay out in the distance a target. We want to convert to hours. From there, we need to decide whether we're multiplying or dividing by each of these conversion factors, trying to cancel out units along the way. We'll see that in this particular way that I've laid out, and you're welcome to sort of guess and check, you're welcome to sort of put units out there, check if the units cancel out. But in this particular case, I can begin to cross out units, seeing that units are divided by the same unit, canceling out that unit, leaving me with only one unit left over. In this particular case, I've decided to multiply by 16 weeks divided by 1 semester. Again, a conversion factor is this ratio, something divided by something. The semester unit divided by the semester unit cancels those two out. With the next conversion factor, I can divide weeks divided by weeks, canceling that unit out. Day divided by day, trip divided by trip, minute divided by minute. Here, make note that I knew that I had to divide by 60, not multiply by 60, so that the minutes canceled out, leaving me with only one unit left over, hours, which of course is my final desired unit. From there, it's quite simple that I can plug into my calculator 1 times 16 times 1 times 2 times 40 divided by 60. So I can take all the numbers. That will give me an answer. My calculator will give me an answer of 21.333, repeating hours. And in this particular case, I'm going to round to about 20 hours worth of travel. Again, this is sort of the result we've been looking for. How many hours will I spend on the T coming and going from class per semester, going from 1 semester to hours through these conversion factors? It may be tempting, particularly for simpler conversion factors, or if you are in need of taking some shortcuts, to not write down all of your work, to sort of just do it mentally, to sort of just put final answers. I highly recommend, I strongly suggest that you write out and show all your work. Write out all your equations just as we have here. Don't leave anything out. If you make some sort of mistake along the way, I can see sort of if you've multiplied or divided by something incorrectly, and I can help you get to the final answer. And in many cases, I can give you partial credit for just sort of a math error. If you don't show me your work, one, you're more likely to make mistakes, and two, I'm unable to help you if I can't see how you got to your final answer. Now, there may be the question of how did I know to round my 21.333 repeating hours to just 20 hours? Well, it's helpful to consider that one of my conversion factors, which is the length of a trip, was really an average that I took, 40 minutes per trip. And it really was an average of an estimate that depending on how quickly the tea is running that day, depending on how busy the cars are, uh, that same trip might take me anywhere between 30 to 50 minutes, a range of values. Uh, and this thing that we measured, the length of the trip, has some sort of degree of uncertainty. It could be shorter than 40, it could be longer than 40, plus or minus 10 minutes or so. Compare that, excuse me, compare that to another conversion factor, something like knowing the number of weeks per semester, which we knew was exactly exactly 16, because we could count how many weeks there were in our schedule, in our calendar, or something like how many minutes there are per hour, 60 minutes, of course, per hour, which is a definition. There's no uncertainty or ambiguity with these two conversion factors that we counted or were part of a definition. Now, in these cases, since we were not super precise about the length of our trip, there is quite a wide range of time, 30 to 50 minutes, for this particular conversion factor, this length of the trip. We can really only round our final answer to something that's equally imprecise. So because our estimate's only 30 to 50 minutes per trip, we would probably only be able to say 20 hours, rounding it to quite this round number. It would be a little misleading to say we knew exactly how many hours it would take, 21.33 hours, because one of our measurements, one of our conversion factors, was pretty imprecise, really having only a single a single number in its sort of defined place. In chemistry, we're really careful about not overestimating or underestimating how precise our final answer, how confident we are in each of the digits in our number. If I say 20 hours, I'm pretty confident in that too. It could be 21 hours, it could be 22 hours, it could be 19 hours, but I'm confident it's in that range of 20 hours. I'm not as confident, and that would be overestimating my confidence, my precision, by saying 21.33, which would indicate a much tighter range, a much tighter window. To keep track of this precision through all of our calculations, we need to consider something we call significant figures. Significant figures really is a feature of the fact that no tool that we use to measure something is perfect. Every measurement that we do with a tool, whether it's a ruler or a scale or a stopwatch, has some level of error or uncertainty. When we talk about uncertainty in science, there's two ways that we talk about it. We may talk about the accuracy of a measurement or the precision of a measurement. When we say precision, which we'll talk more about than accuracy, the precision of a measurement tells us between which two values we are confident the measure falls in. It kind of indicates the spread of that data. We see that in our graph to the right, we see sort of 4 different targets of which someone has shot this target a number of times. We see that here in the looking at sort of the 2 ones on the left, we see that the spread, how far apart each of those dots are, how far apart each of those shots are, is pretty wide. Each individual shot is kind of all over the place. They're kind of clustered around the center of the target, but the spread is very wide. This is an imprecise or not precise measurement or target, compared to the ones on the right, which are all clustered very closely together. There's a very small spread, a very small range of where these shots have landed, being much more precise. The higher the precision, the smaller the potential range of values, or the smaller or more tightly clustered each of those numbers are. This is different than accuracy. We see in this same graph that the two targets on the top are, one is imprecise, one is more precise, not clustered and clustered, but they both are centered around the center of this target. Both of the targets on the top are accurate. They all are towards the center, so towards the true value, the true aim of this particular target. Compare that to the one on the bottom right. We see at the bottom right that all the shots are clustered very tightly together. The shots on the bottom right are very precise, all very close to each other, but not very accurate. They're all clustered not at the center, far off the center of this target. We're very careful in chemistry talking about precision versus accuracy. Luckily for us in chemistry, most of the tools we use are very accurate. They're calibrated, so they're centered on the correct mass or length or time that we want to measure, but they may have different levels of precision, how tightly clustered each time we do a measurement is. What do we mean by this? So let's say you caught a fish and you want to tell people how long the fish you caught is. Well, you may use different types of rulers or different types of tape measures to measure the length of this fish. Let's say you had the top ruler, which only has lines every 10 centimeters. Because we only have lines every 10 centimeters, we probably could confidently say that this fish is somewhere between 50 and 60 centimeters. Because we only have lines at these positions, we can't be very precise about this length, only somewhere between these two ranges. Compare that to the ruler on the bottom, which has a tick mark, a line every 1 centimeter. A different ruler, in this case more precise, more tick marks. And because of the additional tick marks, we can be even more precise and say that this fish is somewhere between 53 and 54 centimeters. In order to communicate how precise the ruler we used to measure this fish was, how confident we are in the precision of its length, we need to record the correct number of significant figures. In this case, for the top ruler, we would write this value as potentially 53 centimeters, versus the one on the bottom we may record as 53.5. When recording data, when recording measurements using these types of tools, we record down the number of measured digits. So in this case, because we could count up through 50 centimeters, we write 5. And we also include one estimated digit, estimating the distance between these two tick marks. So because this fish fell between 50 and 60, it is our prerogative, it's our ability as a scientist to say, we're going to estimate this as being about 3/10 of the way, or around 53 centimeters, one estimated digit between 50 and 60. Again, compared to the one on the bottom, having more tick marks, we could count up to 53 tick marks and estimate one more decimal place, saying it's about halfway between 53 and 54, so we'd write down 53.5 centimeters. We see that the number on the top has two digits, 5 and 3, versus the one on the bottom has more significant figures, 53.5, 3 significant figures. It's important to know that even if we make an estimate that the fish or whatever we're measuring falls exactly on a tick mark, we still record an extra 0 as that estimated digit, because ultimately this is how we keep track of how precise this tool was, how confident we are in the measurements. So make sure that you're recording these zeros, particularly in cases when it lands directly on a line. In Lab 1, we're going to practice this skill as well, but here we'll state it for your reference here and in the future. Let's look at another example. Let's say we look at a thermometer, here measuring the temperature maybe of the room. What about this thermometer? For this particular thermometer, we see that the liquid level in the thermometer falls somewhere between 76 and 77 degrees Celsius. Again, we have a line every 1 degree Celsius, so we can see that we can count the ones place and have to estimate a single decimal point. So because the liquid level falls roughly halfway between 76 and 77, I would record this as 76.5 degrees Celsius. I need to make sure that I don't just record 76, as that would indicate a less precise thermometer. By recording 76, that tells me and every future scientist who looks at that number that my thermometer wasn't very precise. I only had markings at 70 degrees and 80 degrees, and I estimated the 6 that was about halfway between 70 and 80. Again, these sig figs tell us and record how precise our tool was, how confident we are in that particular measurement. In the instance in which we use digital tools like a scale, which sort of displays the number as numbers for us, we don't need to estimate the digit. The scale or the tool is itself estimating the last digit for us. Most tools, like a scale, will also indicate might explicitly indicate the estimated digit. So if you put something on a scale, or so-called mass balance in the lab, it may display 2.334 grams, and you would see sort of on the side, just to the side of the display, plus or minus 0.001 grams. What this means and how we interpret this is that the scale itself measured 2.33 grams and is estimating this for plus or minus 0.001. This scale is estimating that the actual measurement fell somewhere between 2.333 and 2.335. Again, these sig figs and this final estimated digit tells us the range of values that the actual measurement lies in. We're always sort of representing that these tools are imperfect. Sometimes they're slightly high, sometimes they're slightly low, and we give this range to represent how precise, how confident we are in these measurements. Now, why do we care about this? Why do we need to be so persnickety? Why do we need to be so careful about significant figures? Ultimately, it does depend on sort of what our application is, but it's the way that we communicate in critical instances how precise and how confident we are in a measurement. Let me give you an example. Let's say that you are working with a doctor, and a doctor weighs a baby and has you determine an appropriate dose of a very potent drug. Because of how potent this drug is, it's very important that you don't overdose or underdose this baby. You really need to know exactly how much this baby weighs to your best ability. If the doctor very casually, without paying attention to significant figures, tells you that the baby weighs 10 pounds, it's very hard to know, by just sort of saying 10 pounds, what the error or uncertainty of that weight is. But if you were to record this as 10 pounds, to people using significant figures, which is everybody, that would indicate that the baby is somewhere between 9 to 11 pounds potentially. But what if the doctor was more confident, the scale was more precise, and we knew the more precisely that the baby weighed between 9.9 and 10.1 pounds? What if the scale was very, very imprecise, and all we could really say was that by displaying 10 pounds on the scale, it really only estimated it's somewhere between 0 and 20 pounds. Which digit of this 10 is estimated? Is the 0 estimated? Is the 1 estimated, which would indicate between 0 and 20 pounds, or is a decimal point being estimated? In each of these cases, we use these sig figs to make sure that we're communicating exactly how precise these measurements are, because in many cases, using these measurements in calculations, like calculating the dosage of a drug, really comes down to the details, really comes down to a question of precision. Now, quite often, as in the case we were given here, we're going to be given a number that has already been recorded. We may not be able to see the tool, so we don't know how precise the tool is, but we should still be able to interpret from just a number alone how many significant figures there are and how precise that instrument was. Quite often, or there's sort of two sets of simple rules. If I see a number, I know that all the non-zeros, basically any digit 1 through 9, is a significant number. It's a number that was either measured or estimated. The hardest part is to know when there's a 0, of whether or not that was a number that was estimated or measured, or is it simply there as a placeholder as a result of a unit conversion? Let me give you an example. Let's say that I put a weight, I put a coin on a scale. That scale told me 1 gram, one significant figure. Very, very imprecise, meaning that I really know that this coin weighs somewhere between 0 to 2 grams. Imprecise scale, imprecise measurement, wide range of mass, one significant figure. I could also represent that mass in terms of kilograms, and for that same mass, 1 gram is the same as 0.001 kilogram. Just because I've changed the unit from grams to kilograms, this measurement did not somehow become more precise. This unit still only has one significant figure. Those three zeros before the 1 are what we call not significant. They don't represent something that was measured or estimated. They're simply there as a placeholder or the result of a unit conversion. In this case, we still view this 0.001 kilograms as meaning we're only confident that this coin weighs between 0 kilograms and 0.002 kilograms. Again, changing the unit doesn't make it more precise, and quite often when we see zeros in numbers, they are not significant, not a measurement of precision. However, we of course can sometimes have zeros, such as if the length of the fish falls exactly on the tick mark, in which case the 0 does represent an estimated digit, most often at the end of a measurement. In this case, of course, if we, for example, measured 10.0 pounds on a digital scale, this implies that the range of the real weight lies somewhere between 9.9 and 10.1 pounds. This 0, the last 0 at the end, is an estimated digit, giving us 3 significant figures, so 3 things that were measured or estimated in this particular measurement. One reason why we try to use digital tools most often is that it kind of eliminates the need to know a lot of these rules for ourselves. Most often for digital tools, you can simply write down all the numbers that are displayed, but we still need to know how to do this since often we will use analog tools. We can easily see that usually the case is that the more significant figures there are, the more precise the measurement was, the smaller this percent error would be. Again, consider the difference between 9 to 10 pounds, plus or minus 1 pound, versus plus or minus 0.1 pound versus plus or minus 0.01 pound, all representing this range of uncertainty from this estimated digit. By and large, we have a set of rules that we can use to interpret zeros, when zeros are significant and when they are not. Again, any non-zero, 1 through 9, is a significant digit, measured or estimated. But when we encounter a 0 in a number that is presented to us, if that 0 is found between two non-zeros, or it's at the end of a number with a decimal point, that is a significant 0, something that was measured or estimated. So if we have the number 3.02, 3 and 2 are significant digits, and the 0 between the non-zeros, between the 3 and the 2, is also a significant digit, one that was measured or estimated, part of our precision. So this 3.02 has 3 significant figures, as we would tabulate them, as well as if we have 5,280 point, this extra decimal point at the end of this number, means we have 4 significant figures. This is something kind of weird about science that doesn't really happen in sort of everyday life, is that sometimes we might end a number with a decimal point without anything after the decimal point. This is how we indicate that this 0 at the end of 5,280 is an estimated digit that is significant by adding this decimal point, which may look funny, but it's how we communicate that this is 4 significant figures, not just 3. Zeros are not significant if they're at the beginning of number, just as we saw previously with 1 gram to 0.001 kilograms, or if they're at the end of the number without a decimal point. Again, if we see 0.05, these zeros before the non-zero, the zeros before the 5 are not significant, So this only has one significant figure, one number that was measured or estimated, as well as, of course, ones before the decimal point are still not significant, but the ones after a non-zero are. So here we see a weird case in which, with a decimal point, the zeros after the 5 are significant, and as always, the zeros before the 5 are not significant. Some final examples. If I were to just write 200 without a decimal point, because those are zeros after a non-zero, without a decimal point, these are not significant. This number, 200, only has one significant figure, which in many cases would indicate an uncertainty of between 100 to 300. Very imprecise, only one significant figure. Compare that to a number that's recorded as 200.0 with 4 significant figures. Again, these 3 zeros after the 2 with a decimal point are significant. This would indicate a number of 200.0, which would range between 199.9 to 200.1, a much smaller range, more precise measurement, more significant figures. One other little note, again, in terms of notation, do make sure that if you have a number that starts with a decimal point, that you include the 0 to the left of the decimal point. Here you note that I wrote 0.05 and 0.0500. It is often easy to get mistaken if you just write 0.05 or 0.0500. Often the decimal point gets lost, and it's hard to read. So make sure you include the 0 before the decimal point to be the best communicator of your numbers. Why does this precision matter? Well, I gave the example of the doctor and the baby, and that does happen, and that kind of thing does exist. But quite often in science, we need to extrapolate from measurements. Quite often we measure one thing, and we try to measure as precisely as we can. We have to calculate something very, very different. In the same way that we extrapolated from one semester to the number of hours spent on the T, we have to make sure that when we do similar calculations, particularly for very big numbers and very small numbers, that we don't magnify or that we don't lose the error and uncertainty of the original measurement, that error or uncertainty gets magnified or propagated along with the rest of our calculations. We cannot pretend that our measurement is more precise or less precise than it is, as it's quite deceptive, and in many cases, being deceptive in this way is quite dangerous. It can harm people in ways that is unspeakable for most of our consciences. Most often, this takes the place of arbitrarily adding or removing significant figures, changing how we round numbers to make the numbers look better or worse, depending on how we feel. When we do so, when we try to pretend our measurement is more precise or less precise, it is quite dangerous, quite unethical, and in many cases, since many of you are headed into health professions or public-facing roles, it is at the expense of people's lives, monies, and livelihoods. So when we do calculations with measurements, as we did before, going from semesters to hours spent on the T, we have to make sure we preserve the error of the original measurement, that we carry through the correct number of significant figures, and ultimately we know when to round our final answer or how many digits our final answer should be rounded to. For that, we have a couple of rules that take some time to memorize, but we'll practice it again and again. If we add or subtract two numbers, or a series of numbers rather, we first perform the calculation normally. We keep all the digits, we plug everything into our calculator, and then at the very, very end, we round to the least precise digit. What that looks like in practice is that, let's say I added 1.26 milliliters. Here the lowercase m, capital case L stands for the volume measurement of milliliters. If I add 1.26 milliliters plus 2.2 milliliters, I can calculate out a new combined volume. Note that 1.26 milliliters has a significant digit in the hundredths place, the second decimal. But 2.2 milliliters is less precise. It only has a significant digit out to the tens place. In this case, we have two different measurements with two different levels of precision. So I need to round to the least precise digit. What that means in practice is that I first keep all the digits. I plug everything as normal. So I plug into my calculator 1.26 plus 2.2. That gives me 3.46 milliliters. I need to round this number to show that 2.2 milliliters wasn't a very precise volume measurement. And so because 2.2 milliliters is only precise out to the tens place, one decimal place, I must round my 3.46 to one decimal place, or 3.5 milliliters. Sometimes this looks a little ridiculous. So for example, if I have 1,200 grams, in this case, my significant digit only goes out to the hundred place, this 2. Again, zeros after non-zeros are so-called trailing zeros, not significant if there's no decimal place. So this 2 in the hundreds place is my most precise digit for this measurement. If I were to add to that 10.3 grams, a very, very precise mass, a very, very precise measurement, with all the way out to the 10th place. If I add these two and I plug into my calculator, I of course get 1,210.3 grams. But because 1,200 grams was very imprecise, I have to round to the hundredths place, which rounds back all the way to 1,200 grams. Now you may look at this and it may seem ridiculous that I added two numbers together, and I got the same number at the end of it left over. I took 1,200 grams, added something to it, and I still got 1,200 grams. But if you think about it, if I measured 1,200 grams, that really means I'm confident that the mass of this thing is between 1,100 and 1,300 grams. Adding a very, very small amount of mass, 10.3 grams, 1% of that mass, really doesn't change the mass of 1,200 grams all that much. It's such a small mass to add, considering how imprecise that measurement is. And so really, I'm still only confident the value is between 1,100 grams to 1,300 grams, or of course, 1,200 grams with two significant figures. So when we add and subtract, we round to the least precise digit based off of all the numbers we add or subtract together. When we multiply and divide, we again perform the math normally, plug all the numbers into our calculator, and then we round to the fewest number of significant figures. So if I take 2.3 grams divided by 1.224 milliliters, I plug this into my calculator, I get 1.879 ... For future notes, when I don't want to write all the numbers a calculator spits out, I sort of want to artificially sort of put the blah blah blahs. I'll write ... just to show that there are more digits, but I probably will round before that. So my calculator will tell me this value result is 1.879 something 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 grams per milliliter, grams divided by milliliters. Because my 2.3 grams only has two significant figures in it, the 2 and the 3, my final answer gets rounded to two significant figures, in this case 1.9 grams per milliliter. It doesn't matter how precise my 1.224 is, it's more precise, and so we are limited by the less precise thing, 2.3 grams, 2 sig figs. Again, we can see if we go 10.2 grams divided by 5.1 milliliters, we round to two significant figures, in this case giving us 2.0 grams per milliliter. Even if it ends in a 0, as in the case with 2.0, we need to keep the 0 to show that we have two significant figures in our calculation. Again, preserving this level of uncertainty, or this level of precision. So keep the zeros as they are appropriate to preserve and show how precise, how many sig figs the original numbers had. Often, we'll need to do compound math, by which I mean we'll both have to add or subtract things, as well as multiply or divide things. As you do with normal math, we do order of operations, But after each operation, we sort of need to artificially keep track of how many digits we would normally round to, but not round yet. We will only round at the very end of the calculation. Most often, it's sort of helpful to see what I mean by example. So let's say I want to do this calculation. I want to first subtract 7.225 grams minus 0.21 grams, and then divide that difference by 7.2 milliliters. Compound math, two types of operations, two sets of rules. Order of operation says I'll first do the subtraction. I plug that into my calculator. That gives me 7.015 grams. Now, because the 0.21 grams has significant digits out to the second decimal place, normally I would round 7.015 grams to two decimal places, or 7.02. But because I'm not done yet, I'm going to make note that I would round this to the second decimal place, but I'm going to keep 7.015 and use that for the rest of my calculations. I make note that normally I would round to a number that has 3 significant figures, but I'm going to use the full number in this calculation so I don't get rounding errors. Finally, I'll do the second operation. I'll plug in 7.015 divided by 7.2. Because my 7.2 has 2 significant figures, and my 7.015 would normally get rounded to 3 significant figures, I round my final answer to 2 sig figs, giving me 0.97 grams per milliliter. Do make note that if I had rounded early, and I had divided 7.02 divided by 7.2 instead, rounding too early, I would have gotten actually a different answer. I would have gotten 0.98 grams per milliliter. A different answer, really only coming from an error or sort of an overestimated rounding error from this math. So do order of operations, keep track of when you would normally round after each operation, but only round at the very, very end. Now, when we do these conversion factors, when we calculate things in science and in chemistry, there's really two types of numbers you'll encounter, and we treat those slightly differently. The first one is one we've been talking about a lot, measurements. This is something that, again, is measured with a tool. It might be a ruler, it might be a stopwatch, it might be a scale, so on and so forth. But because each of these tools are measurements, they have a certain level of precision, and we need to keep track of significant figures, as we've talked about up to this point. The other type of number that we'll encounter will be an exact number. This is something that is either counted, for which because we can count units of something, it has infinite precision, or something that might be a definition, again, a thing that we count. So when we look at this example from earlier in the lecture, converting from 1 semester to hours spent on the T, we see that we have two different types of numbers, both measurements and exact numbers. We see that we have a series of exact numbers, things that we can count. We count 1 semester, we count 16 weeks, we count 1 day, we count 2 trips per day. These are things that we can count, and we have no uncertainty with how many weeks there are per semester, how many days of the week we go to campus, how many trips we take per day. There's something we count. They are always in integer units. In comparison, we have a measurement, 40 minutes per trip, something we had to measure, sort of getting on the T, starting a stopwatch, ending a stopwatch, and maybe sort of taking an average of several trips. Again, something we measured with a level of uncertainty. Finally, this hour per 60 minutes, again, is something we count, but we can also consider it, we can either think of it as a definition or something that is an exact number. In each of these, we can ignore the significant digits of exact numbers. One way we can think of it is that is infinitely infinitely precise, has infinite significant figures, and in many cases we can just ignore it from considering when we add and subtract how many we round to. Again, measurements versus exact numbers, and problem set 1 gives us some practice with identifying the two different types of measurements. Now, as a final example, before we round out this online lecture, an important place where we see significant figures as an example is when we measure very, very small numbers, such like the very low concentrations of very, very toxic substances. Earlier last year, you probably saw in the news that there was a very catastrophic train derailment in East Palestine, Ohio, one in which a large amount of toxic chemicals were spilled and released in quite a dramatic crisis. Quite naturally, people living in that area, the Environmental Protection Agency, first responders, were very, very concerned with what the concentration of those spilled toxic compounds were, how much of those toxic compounds were in the soil and water. And because they're so toxic, we really need to know not just is it a small amount, because they are still very toxic at low concentrations, small numbers, but when have they fallen to zero? How close to zero do they need to be before we can be safe and feel confident to go back into these areas? We need to know how precisely people are measuring these small numbers, this low concentration, because of how toxic these chemicals are. In this case, it may matter exactly how precise our measurement of this concentration is. Let's say we were worried about one of the compounds that was released in Ohio. In this case, it was a compound called phosgene. Phosgene is actually a World War I chemical weapon that has since been banned in war, but still appears in industrial settings from time to time. And this compound, quite on accident, was released during this railroad incident. It was actually sort of created as part of a first responder set of steps. We'll talk more about this in a little bit. But the residents and people of Ohio were concerned of how much phosgene, a very toxic chemical, was released into the air and water. The EPA knows a lot about this compound, the Environmental Protection Agency, who is tasked with safeguarding our health and understanding how much of a chemical is a hazardous amount of this chemical. The concentration, or sort of the how much of this molecule per volume of phosgene is permissible, is reported as 2 ppm. ppm standing for the concentration unit of part per million. So this represents 2 molecules or 2 parts of phosgene per million molecules of air, million parts. When the EPA says 2 ppm, you'll notice that this number has one significant figure, just a 2. What this really means is that the EPA, because the research is still relatively minimal, the EPA is really only confident that the safe threshold, in which it becomes dangerous to human health, the safe threshold is somewhere between 1 to 3 ppm, a quite wide range centered around this average best guess value of 2 ppm. If we were to measure a concentration of 1.4 ppm, would we feel safe to go back into the contaminated area? 1.4 is numerically lower than 2, but if we understand that this 2 ppm really means their confidence between 1 to 3, we might be uncomfortable that 1.4 ppm still falls within this uncertainty range, still falls within the precision of the EPA's measurement. It would be a different story if the EPA said that the safe limit was 2.0 ppm, representing a different level of precision, maybe meaning it's between 1.9 to 2.1 ppm, parts per million, of which 1.4 is certainly below that more precise critical concentration. Now let's pretend that we are concerned about the amount of phosgene in the air around us, and we hire two different teams of scientists to measure the concentration of phosgene in the air and tell us, is it safe to go back into this contaminated area? The two teams we have Team A, which is a more expensive team. We spend more money, it's more costly, but they have better equipment and techniques, a more precise set of equipment, more precise techniques with more significant digits or more significant figures. We may also consider hiring Team B, which is cheap, very fast, but they don't have very precise equipment. They don't have very precise techniques. What's the difference between hiring these two teams? When might it matter? Let's take a look. Team A, for example, being more precise, might measure 1,200 liters of air. They would report it as 1,200 dot or 1,200 point liters of air. 4 significant figures, all these zeros being significant, meaning that the actual volume of air that they sampled, they're confident lies between 1,199 and 12,001 liters. Very precise measurement, very small, narrow range of volumes that they measured. They have a very precise piece of equipment called a gas chromatograph that detects phosgene and measures how much phosgene there is in that 1,200 liters. And it measures 1.41 milliliters of phosgene. Again, very precise measurement. 3 significant digits out to the hundreds place, meaning that the amount that they are confident they measured is somewhere between 1.40 to 1.42 milliliters. To calculate the concentration, we take the amount of phosgene divided by the amount of air, or 1.41 milliliters divided by 1,200 liters. In the parts per million notation, we want to convert from liters to milliliters. And in those same units, that same number, you don't have to worry too much about this conversion right now. We'll practice this in problem set 1 and 2 actually. 1.41 milliliters divided by 1.200 times 10 to the 6 milliliters of air. Calculating that out in the part per million notation means that the concentration of phosgene that Team A measured was 1.18 ppm. 3 significant figures, a very precise, confident number. We might consider a worst case scenario. Let's say that their estimates were sort of at the high and low end of that little window, of that range of uncertainty. What if they only measured, what if they actually measured a smaller amount of air, 1,199, and a higher level of phosgene, 1.42, at the upper and lower ends of their uncertainty? In this case, because the range of uncertainty, the number of sig figs is quite precise, even in this worst case scenario, more phosgene per less air, we still have a concentration of 1.18 ppm. Again, a very precise number coming from very precise measurements, with many significant figures, means that we're very confident when we say 1.18 ppm. In contrast, Team B, much cheaper, much faster, kind of cuts corners. Instead of 1,200 liters, they only measure 12 liters of air. 12 liters with 2 significant figures means that they sampled somewhere between 11 to 13 liters worth of air. They use a much cheaper gas chromatograph to detect the amount of phosgene, and they measure 0.001 milliliters of phosgene. Again, 1 significant figure. The zeros before the 1, not significant. 1 significant figure, meaning the actual volume of phosgene, this toxic chemical that they measured, lies somewhere between 0 milliliters to 0.002 milliliters. Converting this number in the same math we did the same on the previous slide, this comes out to that they would tell you that, oh, there's only 0.8 ppm phosgene within the air, a much lower number than Team A gave you, but potentially one they're less confident in with only 1 significant digit. Calculating the worst case scenario for this team, if they actually were on the upper and lower end, let's say they actually measured 11 liters of air and actually measured 0.002 milliliters of phosgene, what that would come out to is the actual concentration of the air is actually 2 ppm of phosgene. Again, a less precise measurement, fewer significant digits means a wider range of values, a less confident number at the end of the day. Comparing these two teams between a high precision measurement and calculation, as in Team A, versus a low precision, low number of sig figs calculation in Team B, we can see that there's a very different story that they report. Team A might be very confident in saying that it is potentially safe to go back in, but Team B might be misleading, saying that the phosgene is lower than it is, but with a much higher uncertainty, a much higher and much more drastic worst case scenario, which would be a toxic or potentially dangerous limit. And so here we see a clear case, and we'll see more of these cases throughout this course, of why we care about these significant figures. Hopefully you care about being precise scientists and medical professionals. The trick comes in, of course, into keeping track of these rules in sig figs and keeping track of these rules as we take measurements in lab. The labs we do will provide ample practice for recording data correctly and doing calculations correctly. And the video tutorial for this week for problem set 1 gives some helps, tips, tricks, more examples of doing these calculations in problem set 1. So with that, we'll end our online 1B lecture here, and we'll see each other in the tutorial for problem set 1.